we go, recording. We're going to be graphing rational functions today. And like I was just saying, each of these graphs, there are 4 of them in the examples, and each one has a different shape. This is the one kind of function that you will encounter that you won't really know until you get into it and dissect it a little bit, exactly what shape it's going to have and what's going to happen. And it's going to have some weird features that you don't have on other graphs. So it says identify the points of discontinuity. That means the places where it's not continuous. So that's a little bit of a hint what we're looking at. Holes, vertical asymptotes, horizontal asymptotes, and the domain of each. Then sketch the graph. So there's a lot of information there, but mostly what we're going to be looking at is simplifying the rational expression part of the function and using that to sort of guide what we're doing. All right, so the first step on this, since we've been working on factoring and simplifying these fractions, is to factor and see what that gives us. So on the top, notice it has an x cubed minus 16x. The first thing I want to do is take an x out of that.
And then it's a difference of squares.
And then it's a difference of squares, x squared minus 16. So you're multiplying to get negative 16 and adding to get 0, which would give you x plus 4 and x minus 4. So I went ahead and just did the whole top going across. And then on the bottom, I noticed that I have all even coefficients, and I do have a third power. I've got x's in all terms. So I'm going to take a 2x out of everything, and that'll leave me with x squared plus x minus 6. And that one we can factor also. We're looking for numbers that multiply to make...
Negative 2 and 3.
Good. So the 2x still has to be there. That's going to be an important piece in a minute. So we're going to have x plus 3 and x minus 2. Now, your asymptotes for this function come from any value of x that's going to make the denominator 0. Okay, so remember when we talked about domain, when you had a simple rational function, we would go through and find all the things that x could not equal. That's going to be the first thing that we're going to do.
Negative 3, positive
3. Actually, I take that back. The first thing we're going to do is see if we can cancel anything. So the only thing you can cancel here is the x. And that is a special thing. That won't be an asymptote. But if there's something you can cancel from the top and the bottom, that's going to be a hole in the graph. And that happens where 2x equals 0, which you divide by 2, x equals 0. When we get the rest of the graph in there, there's going to be a hole at 2, which is just you're going to make a little point that's not filled in. And anything that doesn't cancel, then it's going to give us our domain. So you guys were already starting on that. So if I have x plus 3 equals 0, that means there's going to be an asymptote at x equals negative 3. And I'm going to draw that in using a little bit of color. So x equals negative 3 is a vertical line. Okay, like this. And so there's a couple of questions that we can answer now. This gives us a hole. There's a hole at x equals 2. This is going to be a vertical asymptote. I'm going to abbreviate that vertical asympt for obvious reasons. And so that'll give us a vertical asymptote at negative 3, and you're going to want to have that in there before we put in other information. And then the other number that would make the denominator equal to 0 is this piece, the x minus 2 equals 0, which would give us x equals 2, which will also be a vertical asymptote. So do you guys remember why is it not okay to have 0 in the denominator?
Because you can't divide by 0.
Can't divide by 0. It goes off into infinity. Strange things happen. And you're going to get to see that today a little bit better than you've probably seen in the past. So there's a couple of vertical asymptotes right there. Now, horizontal asymptotes, there's sort of a weird trick. So I'm going to show you that. We have what's called the leading coefficient. The leading coefficient, if all of the powers are in order from greatest to smallest, the leading coefficient is the coefficient of your first term. And so up here, there wasn't a number, so that would be 1. And then the leading coefficient at the bottom is a 2. Your vertical asymptotes will happen when you make a fraction out of the leading coefficients of the top and the bottom, which in this case is going to be 1/2. And because they're horizontal, they will be y equals, and so I basically take a 1 from there and a 2 from there, so you have to make sure that they're in order, and that'll give me my vertical asymptote. So I know doing a 1/2 on this small grid's kind of hard, but you go up about a 1/2 from the x-axis, and we draw that in. And this will sort of give us some boundary lines for where the graph is going to go. So there we have the I'm sorry, I called it vertical. I meant to say horizontal. Did I say horizontal?
No, you said vertical.
I meant horizontal. The horizontal All right, so the horizontal asymptote at 1/2. All right, so at this point, we do know our points of discontinuity a little bit. We know the graph is going to have to jump over this and this. And so both of these are going to be discontinuities. And then your whole at x equals 2 is also included with that. All of these are discontinuities. Those are places where the graph is going to stop and then start on the other side. Holes and asymptotes are places where you're going to have discontinuities. Now, this is the point at which the graphing calculators can make this really easy. If you had to do this without a calculator, what you would have to do is you would have to pick values of x on this side, put it in for all of these x's, and then points in the middle part, put them in for x, and points over here. That's how we did it back in the old days when we used to walk 5 miles in the snow, uphill and downhill. Like, we didn't have graphing calculators, and so you just had to pick several points in each section of the graph to do it. The graphing calculators actually are going to help us get the general shape. So let's go ahead and do that. When you type in these fractions, you do have to put the numerator in parentheses and denominator in parentheses. So I'm going to go back to the original fraction. I'm going to do a parentheses, x to the third, have to right arrow, minus 16x, close the parentheses to show that was the top, divided by parentheses 2x to the third plus 2x squared minus 12x. And then make sure you also close the parentheses on the bottom. If you don't, weird things could happen depending on how the calculator interprets this. And then, assuming that you're on a normal screen, you could hit graph. If you are not on a normal -10 to 10 window, you could do a zoom number 6. So I'll show you that. If you push zoom and then you select number 6, that gives you a standard window. And for most of these, I think the standard window will work. And you can kind of see the 3 pieces and how they work. What the graphing calculator does not do is it does not show you those asymptotes, but you can see there's like a little imaginary break there, an imaginary break there, and you can kind of see how that's working out. And we can get the general shape of the graph from that. Now, the horizontal asymptote is right here at 1/2. These 2 bottom pieces are going to stay below that. So when we go in here, okay, I know I'm staying below this, and it would be nice to get a couple of places. We can see it crosses the x-axis at 1, 2, 3, -4. So we might go and put a point like at -4 right there where it crosses, and then it kind of hovers just underneath that asymptote here, and then it gets very steep over here and becomes almost vertical as it approaches on this side. So that's like the first little piece. It keeps going this direction and this direction, but it stays on its side of the line there. It has to follow the rules. This little shape in the middle that's kind of like a parabola, but not quite, goes in here. And so if we just look at where it crosses the y-axis, it's a little bit above 1. So we can just eyeball that and get a quick sketch. It's a little steeper on this side than it is on this side. It kind of flattens out and goes up like that. And then the right-hand side is going to be over here in this piece. And it looks like it's crossing at 4, which makes sense because on the top of our fraction we had the x plus 4 and the x minus 4. And here's our pieces. Now, hopefully you're all using pencil because there's one more piece we have to go back and add back in, and that is the whole at x equals 2. Remember we had a whole at x equals 2. Was that right? Or I'm sorry, you know what I did? I divided 0 by 2 and got 2. That should be 0. You guys probably wrote the right thing down. I didn't.
No.
You were just going along with me. So when you divide 0 by 2, you should get 0. So that hole's at 0. So where this graph appears to cross the y-axis at a little bit more than 1, we're going to make a little hole right there at 0. And then it's just like a little hole in the middle of that U-A shape. And that's the other piece that the graphing calculator does not give you. Now, if you go into the table, if you do second graph and go into the table, I don't know why I'm all the way down at 20, but you can tell at 0, it says error. Now, it doesn't tell you in the table if that's a hole or an asymptote, but you can kind of tell where the asymptotes are from over here. And so that's a little feature you can kind of use. Did I do that right? Yes, I did. And then where it hits 0, you know it's crossing the axes. And you could actually get some points out of the table feature if you needed to have a super accurate graph. If you were working for NASA, like in the movie, and like you needed a super accurate graph and you needed to know exactly where everything was, well, you could use this to get some more accurate points. But this is good enough for what we're doing. All right, so let's see if we've answered all the questions. So we identified the points of discontinuity, the holes, vertical asymptotes, horizontal asymptotes. We've sketched it, but we have not done the domain. So the domain is basically the same thing as the discontinuities, except you're going to say that the domain x will not equal 0, x will not equal -3, and x will not equal 2. Like the domain is all real numbers except for those. That's just easier. If you remember from back when we did the interval notation, you could get fancier than this and say, okay, the domain goes from -infinity up to -3, and then goes from -3 to 2, and then goes from 2 to infinity. You can totally use that notation and go from left to right.
0 and 0 to 2.
Oh yeah, I'm just having a hard time. Thank you. And
like
then,
the
oh wait,
other
so -3 to 2. No, that's right.
Wait.
No,
Is
oh.
it 0?
Oh, there is a break at 0, so I'd have to put 0 in there also. So I'd have to have 4 groups to write because of the whole. So -3 to 0, and then 0 to 2, and then 2 to infinity. Did I get it right that time?
Yeah,
Except I
yeah.
forgot the little u. So this is like the long way of writing that. So most of the time, they'll use a notation and basically tell us what parts of the domain it's not, because it's just easier to tell what's not there than what is there. It's kind of like reporting attendance. It's easier for me to tell Miss Arthur, by the way, Kara and Kayla are gone, than it is to tell her everyone who's here.
Yeah.
Sort of the same concept. Okay, so we are done with number 1. These do take a while. Okay, so let's go down to number 2. I'm so glad you're excited. So our first step is to factor everything. So on the top, we can take an x out first, which would leave us with x squared minus x minus 12. And then you can draw the little x if you still enjoy that. We're multiplying to get -12 and adding to get -1.
-3 and 4.
So -4 and +3. It's going to get -1. This one's got to be negative. Okay. Yay, I won one. All right. So then if we go down to the bottom, we can take a 4 and an x out of both. And that'll leave us with x plus 3. And that's as far as that goes. So I'm just going to copy that over here. So to find our holes in the graph, we find the things.
3 cancels.
So the x plus 3 cancels. And so that means we would have a hole where x plus 3 equals 0. Which would be at -3. Subtract 3 from both sides. So that's a hole. And then you could also cancel out the x's over here, which means that we would have a hole at x equals 0. I guess I don't really need that 4 in there. So you'd have a hole at -3 and at 0. And we have to draw those in kind of when we're done with everything else. Then when we look down here to see where the asymptotes are, all we're left with is 4. Doesn't have any x's. What that means is there won't be any vertical asymptotes because there's nothing in the bottom that can make the denominator 0 once you take out the wholes. So it's just going to be wholes. So that's interesting. So let's look and see at what we actually have left. We have, if you just rewrite it after taking these out, x minus 4 divided by 4, which I could write as 1/4 x minus 1. Oh my gosh.
Oh, that's linear.
Slope-intercept form. We don't even need the calculator. We could start at -1 and do a slope of 1/4, up 1 over 4, up 1 over 4, and just put in some points. I mean, you could use the graphing calculator, and then I need to remember where the holes are. So if I like to draw it and then make the holes. I don't know why. That's just how my brain works. So there's a hole at x equals 0. So here where it crosses the y-axis, right there, I'm going to make that a hole. And at x equals -3. So I'm just going to kind of eyeball it. -3, it hits the line about here. So where it crosses that line at x equals -3. So make sure it lines up with the -3 on the x-axis. We have 2 holes right there. So we don't have any vertical or horizontal asymptotes, so we could just say no asymptotes. Okay? And then for the domain, we're just going to say, okay, it's all real numbers except x does not equal 0 or -3. And that one is done. So I told you each of these was going to have a different shape. Yeah, and there's just no asymptotes or anything in there to really worry about because it comes out linear when you get rid of everything. It's linear except it has these 2 holes, and those 2 holes are what make this not actually a normal linear function. It's a rational function because it started with a fraction. Okay, let's go ahead and start number 3, knowing that we're probably going to have to do number 4 tomorrow, but the less we leave for tomorrow, the more time we have to work on this tomorrow. So let's go ahead and factor this fraction. So in the top, I notice I can take a 2 out of every term, so that would leave me with x squared plus 5x plus 4. And then I can factor that further. Good, 1 and 4, so x plus 1 and x plus 4. And you can still make the little x if you need to, but it multiplies to make 4 and adds to make 5. My 2 looks weird. And then on the bottom, this is just one of those that you could do with the x. So yeah, it's just going to be x plus 3 and x minus 1. Multiplies to make -3, adds to make 2. So if you wanted to down here, you could like do your work. Oh, -3 and 2. Oh, it's going to be 3 and -1. And then there is absolutely nothing that cancels. So what does that tell us?
No, what about the x one?
There's no holes. So that means there's no holes. No holes in the graph. We're just going to have asymptotes. And then how do we figure out where those vertical asymptotes would be? So then we take, to figure that out, we have x plus 3. We want to see where that's 0. So x plus 3 equals 0 would give us -3. And then x minus 1 equals 0 would give us 1. And these are both going to be our vertical asymptotes. And so we can go ahead and draw those in. So at -3, I like to use a different color for that just to show it's not actually part of my graph. And then at 1. So there's our vertical asymptotes.
But the vertical one's always on the bottom.
Yes. And then to find the horizontal asymptotes, we take the leading coefficients of the top and the bottom and make a fraction. So I've got 2 here, and this would be 1. So my horizontal asymptote on this one would be 2 over 1, which is, I'm sorry, I have to put the y equals. It would be horizontal asymptote. I'm having problems today.
Y equals 2.
Y equals 2 over 1, which is just 2. And so we would make a horizontal little dashy line up here. So it's divided up like number 1 was, but what's going to be interesting is when we look at the graph, this is going to have a different shape than number 1 did. So there's a vertical asymptotes and a horizontal asymptotes, and if you want to just put points of discontinuity, draw little arrows, all of these, like really, you know, where are the points of discontinuity? That's your holes and your asymptotes. Or actually the horizontal we don't have to list, just the vertical, I'm sorry. So just the vertical ones are actually points of discontinuity because it's talking about the domain. And we could actually go ahead and do the domain before we graph too. We'll just get it all done. So the domain, it is all real numbers except x cannot equal -3 or +1 because that's where the breaks are left to right and we didn't have any holes. So then we'll grab the calculator and do this one. And so remember to put parentheses around the numerator and denominator. So 2x squared plus 10x plus 8 divided by x squared plus 2x minus 3. Don't forget to close your parentheses and open parentheses and all of that. If we go over to the graph, we get kind of an interesting looking
How do I get a standard?
thing.
6.
Zoom 6.
That is really wonky.
It is really wonky. But you can kind of visualize looking at this where those asymptotes are. There's the break there's the break there, and then there's a break up here.
Then why is it crossing?
That's interesting. It's because this piece didn't have the same boundaries as the other. I've never been good at explaining why this one gets to cross that asymptote, but it's more of a boundary for these pieces than it is for that. So we could kind of figure out where this first piece crosses at -4. And so it's like this. Draw little arrows to show that that keeps going. And the middle piece to me looks a little bit like a cubic. Kind of comes down and around. It looks like it crosses the x-axis at -1 and the y-axis at -2 or -3.
-3?
I would
-3.
say negative.
Somewhere in there. We could tell for sure if we look at the table. So at 0, it's actually -2.66666. So really close to -3, which will just make it a little bit higher.
Just watch that episode of Bob's Burgers.
Okay, so then we're going to draw that graph, that middle piece of the graph in.
So funny.
So it'll look something, so this bottom piece looks like this, kind of, sort of, and it comes up
I'm really good at having.
and changes somewhere up here. So we have that middle piece, and then the last piece is all up here. And we could get a couple points since it's floating so high. Go into the table. 2 is at 7.2, and 3 is at 4.66. That just gives us a couple of places we can connect. At 4, it's at 3.8. So it kind of goes down slowly once you get over here. I like to have a couple of points just to give the general idea. And that's the graph. There's no holes. So we've got the points of discontinuity. We did the domain. We did the graph. We know there's no holes. And we got the asymptotes all taken care of. So that's it. What do you say? Should we just do number 4?
No.
Okay. We'll save it for tomorrow.
Yeah.